Okay, this is a worked example to illustrate moments. This one is a plank AB of mass 12. Let me just say that all this first part here basically is just giving you information in which to populate your diagram. And I do recommend that you draw your own diagram. You don't try scrawling on this thing. You actually draw your own. I've cheated slightly myself because obviously I've kind of done a cut and paste on this job, but you won't be able to do that if you're in an exam. So yes, draw your own diagram. Make sure all the forces are marked clearly on it, and the other parameters that you're going to need, in this case the lengths. Okay, right, so let's just go through and let's just make sure we've got everything on the diagram. A plank AB has mass 12 and length 2.4 meters. Here we've got that. The 12, it's got mass of 12 kilograms, so that means this force is acting downwards with a force of 12 G newtons. Later on, he does say that it's modeled as a uniform rod, which means that the mass, it's got the same kind of density all the way along. So the mass is actually acting at the center point, and therefore the force is acting from that same point there. A load of mass 8 kilograms is attached to the plank at point C, where AC equals 0.8 meters. So that's that 0.8 meters. There is the mass. It's got 8 kilograms, so that results in a downward force of 8G. And it's held in equilibrium, so there's no movement, there's no turning, there's no rotational or no vertical movement, or horizontal if it comes to that, by 2 vertical ropes, one attached to A and the other attached at B. Here we go. And now those will be exerting a force on the beam, on the plank, and we don't know those at the moment, so those have been shown as TA and TB. The plank is modeled as a uniform rod, as we've said. The load is a particle. That's a simplifying assumption. It means that the weight is acting just from one point, and the ropes is light in extensible strings, which means they don't stretch. But it also means that the tension is the same throughout. Okay, so the first part is find the tension in the rope attached at B. Okay, so this is relatively straightforward. Because what we're doing is, if we take the moments, we can take the moments about any point, but in order to resolve this most simply, then if we take the moments about A, then we're eliminating this force. Okay, so we basically end up with an equation which is in TB. So if we take the clockwise moments, then we've got the force times the distance from our point of reference. That's 8G times 0.8. We've also got this 12G acting at 1.2, so center point, 1.2, so it's 12G times 1.2. And then the anti-clockwise moments, and these must be equal because it's in equilibrium, is going to be this force of TB times the distance at which it applies from our reference point A. Just to mention, of course, your reference point doesn't have to be any kind of fulcrum or anything like that, or pivot. It could be any point. So that would from A, that's 2.4. So we've got this now. So if we just work this through, I will not go through the working of the equation. We can simplify all this. Gives us 52G divided by 6 is TB. It's just an equation in TB, and if we're using 9.8 meters per second for our value of G, which would be the normal kind of default value to use, then that's going to give us a value of 84.93 recurring newtons as this tension here. Okay, so that is that. Just wind on a little bit. because now we've got part B. The plank is now modelled as a non-uniform rod. With the new model, the tension in the rope attached at A is 10N greater than the tension in the rope attached at B. So what we've done basically is this 12G, which is the weight due to the mass, has moved somewhere. We don't. It's kind of moved away from the middle. We don't know. So we're just going to call this X as a kind of holding measure, and it's not going to be 1.2 anymore. So how do we resolve this one? Right, now, one thing we mustn't forget about when we do these moments problems is that we are still entitled to use our vertical aspect of the forces. And since this beam is not moving, we can look in a sort of a linear sense at all the upward forces and all the downward forces. And in which case we can see that actually the sum of these two tensions is going to be equal to 20G. Moreover, says in the question, the tension in the rope attached to A is 10 newtons greater than the tension in the rope attached at B. So TA is therefore equal to TB plus 10. So TA is the bigger one, isn't it? The rope attached to A is 10 greater than B. So TA equals TB plus 10. And as a result of that, we can actually, we basically got simultaneous equations there. We can eliminate TA, which put TB plus 10 in for that. And that's going to give us that. And that will give us this here, TB equals 10G minus 5. No, I've not actually substituted 9.8 in there. In this case, it wouldn't make a great deal of difference, but as a general principle, keep that constant until later on in the working, because you may well find there's cancellation or factorization or things that might make that a bit simpler. So it's kind of convenient. And the other thing is probably dealing just with something that's simpler to write rather than some decimal to three decimal places. Okay, so having established TB, we can now, if we take the moments about A again, then if we look at the same thing, really, these are the clockwise moments. That's the 8G force. This is the 12G force, which of course is acting X from the reference point. And that's going to be equal to the anti-clockwise. This is B times the distance, and plank length is still 2.4. So what have we got? Right, well, here we've got an equation in X. It's got some G's in there to resolve. But quite simply, we can just work that through. I'll assume that you can do the algebra and the simplification, and that's going to give us this figure. And that will be, when we work this out, substituting 9.8 in there, then we're going to get 1.3646 meters for this distance X. That's to 4 decimal places. So that's basically how it works. As with all these, nice clear diagram. Preferably leave the units off, although in this case the meters was already on when I copied it across, but normally I'd leave the meters off. And don't forget that you're quite entitled to use the linear directions to resolve forces, and you don't just have to rely on the moments. And also do remember that, of course, when you're choosing a place, a reference point, then try and consider which force you might want to eliminate and not need to take into account. So that's that. So hopefully you've found that useful. Okay, and we'll see you next time.